This is our second video on torque, and I mentioned in the first video about different formulas for inertia, and I asked you to remember two main ones. One is for the disc, and the other one is for the hoop. If you Google, or maybe I will include, I'm not sure if it's gonna work out, include it in the description, the Samnos Miller presentation videos on rotational motion. He has explanation about hoops and discs, the one that you will never forget if you watch it, that video. But on the right top side you can see the hoop and the disc rolling down, and because the disc has 1/2 of the inertia of the hoop, it will reach the bottom of the incline faster. Inertia means the resistance of motion. So if you want an object, let's say you have a truck and you have a bicycle. Truck has more mass than the bicycle, and in order for you to change the truck's velocity, you have to apply more force. But if you apply the same force, let's say these two hoops, the hoop and the disc were the same mass. If you apply the same force acting on both of them because they have the same mass, the hoop is going to be slower to change its motion than its velocity than the disc. So the disc always wins in this situation. We also will look at this type of question in our video today, and I believe one of the question is similar to this one. I think there is a man sitting on the chair problem. But you can see the different type of inertia for different objects. You don't have to memorize others. These two, the disc and the hoop, are the main ones. But we're going to look at some questions and see how we can use the information that we learned in the first video and a little bit what I just talked right here to solve problems. So here's the first question that I want to look with you at, and a solid sphere of mass m is fastened to another sphere of mass 2m by a thin rod with a length of 3x. The spheres have negligible size and the rod has negligible mass. What is the moment of inertia of the system of spheres as the rod is rotating about the point located at position x as shown? And because there's happening this rotation, you see the masses are located on the outer sides of the motion. So I can look at it as if it was a hoop. So if I look at it as if it was a hoop, I can find its inertia. That is what they ask me, moment of inertia, by m. The distance for the first one is x squared. It's mr squared, about the point of rotation, plus 2m and 2x squared. So I'm using this formula for the disc, mr squared, for the hoop, right? For the hoop. So, and if I calculate what moment of inertia is equal to, I'm gonna get 9mx squared. Here's another question in this problem, and I'm going to give you time to read it because it's a big problem and I don't want to spend time reading the question for you out of the time that we have to make this video. So go ahead and pause it, read the video, and then when you unpause it, you will see everything that is given, written, and the formula, so you can understand what and how to do this. So here what we have the given masses and the mass of the one that is sliding, the mass that is the one that is falling, and the mass of the pulley. And because the pulley is a disc, then its inertia, moment of inertia, is equal to 1/2 m sub 0 v r squared. And so from this information, I have to find the final angular and linear velocities. So I'm going to use conservation of energy because as the mass going to be falling down, their acceleration is changing, so I cannot look at specific times. So I'm going to use the the energy that I have before is going to go to the energy that I will have after. So the energies that I have before, so at the moment when it starts, the energy that I have before is the potential energy of the block M, because it's some height, the distance d away from the where it's going to be at the end. So if it ends up at this position, then it moves the distance d. So because it has moved this distance, it had potential energy, and it will go to the kinetic energy. And the three masses, all three of them have initial kinetic energy. So for each mass, I have initial kinetic energy. And the hoop one, the one that has m sub 0, or the disk one, the one that has m sub 0, that one also has rotational kinetic energy. So if you remember from the previous video, we had rotational kinetic energy. Maybe I'm going to write it right here. Initial energy of the disk is equal to 1/2 its inertia and omega squared. And I think we also need to remember about relationship between the angular velocity and linear velocity. So the linear velocity is equal to r angular velocity. So we will use this little trick in this video as well. So we have this much potential energy, but not all this energy is going to be turned into after energy, because some of the energy is going to be taken away by the work done by the friction, because there is friction acting on the mass. So the work done by the friction. And then all of this is going to be equal to after. So maybe I'll delete before. So this was our before, at the moment before the mass fell down the distance d. And then afterwards, we will have kinetic energy of the of all three masses. So we have all this above. So all this above is equal to all this, So I have energy before is equal to the moment to the energy after. Now I'm gonna plug in my formulas into the potential energy, to the kinetic energy, and everything else that I need to have in my equation. So here what I have, potential energy of the mass m that is falling down is mgd. So that's by how much its energy changes. Then, or how much it has before it loses it. Then I have the kinetic energy of the mass m, because it has some velocity. Then I have kinetic energy of the mass m that is falling down. Then I have the kinetic energy of the rotational of the pulley. Then I subtract the work done by the friction, which is mu times n, and n is mg, and then times the distance it travels, which is d. Then on the other side, I have kinetic energy final for the mass m that is sliding, kinetic energy final for the mass that is falling down, and the kinetic energy of the pulley that is rotating. So before, we didn't have to think about the pulleys, because pulleys were, every single time we had a pulley problem, it would say it is massless. But this one is not massless, and they give you the radius, so they want you to find the inertia. And in this question, I have to plug in my inertia. So the formula that I wrote where the diagram is, the inertia, I'm going to plug it in instead of my inertia. So the next equation I'm going to write, I'm going to plug in everywhere I see inertia, I'm going to plug in inertia. And I'm going to times every term by 2 so I don't have fractions as well. So I plugged in inertia. So instead of I have, maybe let me choose different color here so I can show you. So I have I right here. And instead of inertia, I plugged in 1/2 m sub 0 r squared times omega squared. And then the same I did for the last term. I have 1/2 and m sub 0 r squared, and then I still had omega squared. But r times omega is v. So instead of having r times omega 0 and r times omega, this one is final. So this one is the final for us, not initial. So that means final. And instead of having R omega, I can just write V. So my next step is going to be to replace R omega with the V. So here I replaced R omega, the one that I had above, with V sub 0 because V is equal to R omega. And I replaced R omega V final with V final. And they asked me to find the final velocity. So to find final velocity, I'm going to solve the next equation for V final. At first, I'm going to multiply them all by 2. And then after that, move all V final on one side, or factor V final, and then move everything else to the other side. So let's start with multiplying every single term by 2 to get rid of the fraction again. So I times every single one of them by 2. So when I times the first one by 2, it became a 4. When I times these terms by 2, m sub 0 became without 1/2, but the other terms have 2's in front of them. And they all had V sub 0 squared, so I took it out of the parentheses. Then I times my red term, the friction work done by friction by 2 as well, became 4. And on the other side, I did the same. I noticed that all of them have V final. I took V final out. And then the first mass times by 2 gives me a 2. And then the second term times by 2 gives me a 2 in front. And the last term times by 2 gets rid of the fraction, and I have m sub 0. Now, if I plug in all my numbers, then I will get V final is equal to 1.64 meters per second. And here that all the information that we had, the mass, the sliding mass, the lowercase fallen mass, and then m sub 0 is the disk, and then the radius of the disk, the friction, initial velocity, distance. We didn't have distance yet. Oh yeah, we do have a distance in potential energy, so we have to plug in that one. So if we plug in all those numbers, we will get final velocity is equal to 164. And from this formula, again, back to that formula, very useful formula to remember. It's not given on AP exam. I can find final angular velocity is equal to final velocity divided by the radius, and the radius is 0.03. So that gives me 54.67 radians per second. 54.67 radians per second. So that was pretty complicated question, I would say. With conservation of energy, you have to be very careful when you simplify from one step to another. You have to be careful when you plug in the numbers into the problem, but it's a very good problem to look at and know how to solve. Here's another question that I even seen something similar on AP exam once, and I think this is very important to understand how to solve this question. So let's do it together. Again, I'm gonna give you time to read it, write down everything that is given, and it would be nice if you did it at the same time with me, because if you try to solve it on your own first before I solve it, I think by now you should have some information how to be able to solve this problem. I'll give you a clue a little bit. It's a conservation of angular momentum. Momentum before is equal to momentum after. So you've seen the skaters, they put their hands far away when they start spinning, and then they bring their hands toward themselves and start spinning faster. So it's the same concept. They lose inertia and gain angular velocity. So it's conservation of angular momentum in this question. So go ahead, pause it, read the question, write everything that is given, see from what I said if you can set up anything to start with, and then unpause it when you have already something in your paper, and then let's look at it how to solve after that together, and maybe you already did solve it right by then. So let's pause it for now. So here I wrote everything that is given. You have two masses, so I'm gonna take 2 times 3 kilogram, and they're on the outer side of rotation, so that means they are like a hoop. So inertia of those two masses is gonna be equal to the same as for the hoop, which is mr squared. So you will have initial inertia, which is, there's two masses, so there's 2m times r initial squared, and you will have the final inertia of those masses, which is 2m times r final squared. So I'm gonna say initial angular momentum is equal to the final angular momentum. So momentum before is equal to momentum after. Initial momentum includes the man and the masses. So I'm gonna say it is initial inertia times initial velocity for the masses plus inertia of the man and the velocity of the man initial, and the final I have initial final inertia when he brings the masses closer, the final velocity plus the inertia of the man, which doesn't change, the stool and the man don't change their inertia, and times the velocity final. And now I'm gonna plug in inertia initial and inertia final into my formula, the one that I just calculated at the bottom on the left side. So I plugged in my inertia and I took the omega sub-zero out, and I plugged in my inertia and I took the omega final out. So now I can solve for omega final. If I plug in all my numbers, I will get the omega final is equal to 1.91 radians per second. And then they ask you to find the angular kinetic energy of the system before and after. So to find the kinetic energy before and after, let me rewrite this in, let's do it this way. We're going to do kinetic energy, I'm going to do it right here. Kinetic energy initial is equal to 1/2 rotational, so inertia, which is initial inertia, r sub-zero squared, times initial velocity squared, plus kinetic energy of the man, which is 1/2 inertia of the man, and initial velocity squared of the for the man as well, the same one. If I plug in my numbers, I'm gonna get 2.53 joules. So that is my kinetic energy initial. For kinetic energy final, I have 1/2 inertia for the masses when they are closer to the center, which is 2m, and r final squared, angular velocity squared, plus final, plus 1/2 inertia of the man, which doesn't change, and then we have final angular velocity squared, which gives me 6.4 joules. And here you see that energy before is not equal to the energy after, and because energy would be conserved if the system never had a matter or energy added into the system, but because man is applying the force of his arms to bring those masses closer to himself, so he does add additional work to the system, so that is why these two energies don't match. So this is very good problem to understand because it can be written different ways, and also it was on one of the AP questions in the past that I have seen. Good to know how to solve. Here's one more question that I want to solve in this video, so go ahead again and pause it, write down everything that is given so you have it in front of you if I have to scroll with my problem solving, and also try to solve it on your own before you see my solution. So go ahead and pause it right now, and when you unpause it, you will see already the information written on the board or on the screen for you. So in this question, we have a mass falling down, and in this case, we have also the disc as a pulley. So the pulley has inertia. So the pulley's inertia it's a disc, so it's 1/2 its mass and r squared. So the radius is given, the mass is given. And also, to start this question, let's write the forces at first that are acting on the mass here. So we have the force mg, we have the tension, and if I look at the disk, I have tension is causing the torque or rotation of the pulley, and there is acceleration. So in this case, the mass is not of the pulley is not negligible, so we have to count the mass to solve this question. So what I'm going to start this question with is by saying that the sum of all the forces is equal to ma, and sum of all the torques is equal to inertia times acceleration. So the forces that I have acting on the mass is T minus mg, and equals to negative ma. And for the torques, I have T is the force, so it's T times r, the distance, and sine theta. So it's T, r is the distance, sine theta, the angle between the radius and the tension force is 90 degrees, so sine of 90 is 1, so I'm just going to skip that part, and equals to 1/2 inertia of the disk, mr squared, and times omega. Then I can see that I can cancel one of the r's from both sides and find from here the expression for tension. Tension is equal to 1/2 the mass r times alpha. And if you remember from our first video with the or for angular motion video, that I showed you that linear velocity again is equal to r omega, and angular acceleration, linear acceleration, is equal to r linear acceleration. So here I see r linear acceleration, so I can rewrite this as 1/2 m and linear acceleration. And then I'm going to plug it into my first equation, because I have a system of two equations. I use two equations to solve my problem. So now I'm going to have, instead of t, 1/2 ma minus mg equals to negative ma. And if I times them all by 2, I'll have ma minus 2mg equals to negative 2 ma. And solving all of this for a will give me the expression of 2m g divided by 2mg divided by m plus 2m. So if I plug in my numbers, I will get a is equal to 4.9 meters per second squared. And then after this, I can use this expression to find angular acceleration. So angular acceleration is equal to linear acceleration divided by r, and angular acceleration is going to be equal to 24.5 radians per second squared. Here's one more question we're going to look at. A wrecking ball of mass 4,800 newtons or 480 kilogram is supported by a boom which may be assumed to be uniform and has a weight of 3,600 newtons. As the figure shows, a support cable runs from the top of the bottom to the tractor. The angle between the support cable and the horizontal is, so this angle right here is 32 degrees. So right here we have 32 degrees. And the angle between the bottom and the horizontal is 48 degrees. So this angle right here is 48 degrees. and find the tension in the support cable. So I'm gonna start by redrawing my boom. So here is the boom, and the forces that acting on the boom, here is the tension. So I'm gonna write the cable. So here is the mass hanging, and this is gonna be the point of rotation. So the forces acting on the boom, there's gonna be some horizontal force, I mean this one, and I'm gonna call it Fx. And there's gonna be some vertical force, I'm gonna call it Fy, so Fx and Fy. Then there's going to be the mass of the boom itself, the force of gravity on the mass of the boom. Let me call it mg. This mass has mg, and it has the tension. And then also there's going to be tension this way, or I can say tension that way. And to make it simpler, I'm just gonna erase this part right here. And I'm gonna say that this way I'm having down right here, I'm having the force acting of it is mg, and by mg I mean 4800 newtons, and by capital mg is 3600 newtons. That's the weight of the beam itself. So these are the forces acting, and I'm gonna use the in the angles, I have 48 degrees, this one, the yellow angle, and the green angle right here is 42 degrees, because if we look at this triangle, and if this one is 48 and this one is 42, together will give you 90 and another 90, together 180 degrees in the triangle. So this one at the top is 42 degrees. And the gray angle right here is 32 degrees. So I have 48 degrees, 42 degrees, and I have 32 degrees. So I'm gonna use the sum of all the torques is equal to 0, and my point of rotation is gonna be the blue point, this one, and it is the force times the distance times the sine angle, but Fy and Fx, I have 0 distance to the point of rotation, so I don't have to include them into my torque formula. So the only ones that I have is negative mg, because it causes the boom to rotate in clockwise direction, in the negative direction, times the distance, which is L over 2, and then I have sine of 42 degrees. And the next force I have also negative, that is mg, and this one is the distance L, and sine is also 42 degrees. And the last one I have tension, but that one is positive, so I have plus, and then I have tension times L, and now I have sine of 32 degrees. Actually, this angle is 32 degrees, sorry. So this angle that is given 32 degrees, so the gray one is 32 degrees. Then the bottom one is not 32 degrees. So there are 3 angles that make this. So this one is 42, this one is 32, so wherever is left is 16 degrees. So this angle right here is 16 degrees. So that will give me a sine of 16 degrees. And all of it is equal to 0. Because they all have L, I can cancel every single L right here. And then I can solve for tension. So let's times them all by 2 and then solve for tension. And so after I solve for T and plug in all the numbers that are given, so I have my tension is equal to 16022 newtons. So 16,022 newtons is the tension in the cable. And that's going to complete our lesson for this video, for the examples that I solved for you. I hope you enjoyed them. I hope you understood them. And thank you for watching this video. I'll see you in the next one. And follow the description, in the description, the link for the next video or for the previous videos if you want to watch and continue learning with these videos.